Hello everybody, my name is Umili and I'm going to present DeepDFA Automata Learning for Neural Probabilistic Relaxations. This paper is accepted by ECAI 2024, and you can read the preprint on archive, and it's a joint work with Roberto Capobianco. So in this work we propose a new neural model that we call DeepDFA to address the problem of deterministic finite automata induction from a set of labeled traces. So this problem is very known in the literature, and it was approached with different kinds of methods. The first class of methods is the combinatorial one, that are usually exact, so they have optimal guarantees to find the right target DFA. But as counter, we have that in practice, they scale very poorly on bigger DFA and bigger datasets, and they are generally unable to handle errors in the dataset. Actually, use this kind of methods in realistic application, it may be tricky. Another more recent approach is the following one, the DFA extraction from pre-trained RNN. This new method is based on first training a recurrent network, an RNN, on the data that we have, and then extracting an equivalent DFA from the trained model. The advantage of this approach is that it scales better and it's more resilient to errors because it's based on neural network. But as counter, we have to decide which neural network to train on the data. That is not trivial because there are many hyperparameters to be fine-tuned. For example, we have to choose which model, which RNN model to train, how many layers to put in the model, how many neurons in each layer, and so on and so forth. Our approach is a neurosymbolic approach instead. We define a neural network that is not simply an RNN. It is a new neural network with a specialized design for automata learning. And this network is softly discretized at training time. So at the end, the model that we extract from the neural network is no longer continuous, is discrete, and is a DFA. So we have a model that is scalable and resilient to errors. At the same time, the only other parameter that we have to fine-tune is the number of state, the maximum number of state of the DFA. So our method is inspired by Probabilistic Finite Automata, PFA. The intuition behind our work is that PFA are easier to be learned with a neural network because a PFA can be represented in a matrix form, and the next output and next state can be calculated by multiplying vectors and matrices, basically as neural networks do. DFA also can be represented in the same form, with the difference that if we represent a DFA in this way, we will have a matrix having only one out vectors as row vectors of the matrix. So basically what we do is we define the DFA as a parametric PFA in which we can drive the representation to be close to 1/0 during training by using some special activation function. So we not learn directly a DFA, we learn a PFA that is discretized at the mean time. And this discretization is obtained by using a softmax with temperature and sigmoid with temperature. So where the temperature tau express how much the output will be close to a discrete output, will be close to 1/0. So here we have the results. We test our framework on target DFAs of different sizes, 10 to 30, and with a number of symbols from 2 to 3. In this table, you can see the results. We compare DeepDFA against ESTA extraction, which is a method for DFA extraction from a pre-trained RNN. We compare also with DFA inductor, which is a stat-based exact method, and with DFA generator, which is another neurosymbolic method. And our approach significantly outperformed all the baselines in terms of test accuracy and number of states. So the number of states of the predicted DFA is the closest one to the target number of states. And it's also very fast and very light. On the right, we show some ablation studies. It can tolerate an error rate in the dataset that is up to 15%. Another ablation studies is the fine-tuning of the state space. And as you see here, the model demands a state size that is bigger than the actual number of states, but it maintains top performances even if the state size set in the model is very big, so it is markedly overestimated. So this is all from my side. Thanks for your attention. Goodbye.